So, welcome to the latest edition of the CODA Plugging Away podcast, your go-to source for in-depth discussions and insights into the world of oil and gas decommissioning. We're delighted today to be having a conversation with the good people from OLEOLOGY, who will fill us in and share a lot of their thoughts and expertise around management of the materials with which they work. So to get that started then, if I can just work around the room and get people to introduce themselves and who you are, then as we go forwards, you won't need to have your voices and say, my name is so-and-so. So,
well, Norman, Paul Callaghan's my name.
My name's Francis.
Well, if you would go by Norman, that'd be a whole lot better. Retains an anonymity. Well, Francis, my name's Paul Callaghan. Director at OLEOLOGY, where we do a lot of standard things. We provide people solutions for oil and waste management, but principally we're an innovative research and development company taking technologies into fields that they haven't been before, utilising those technologies to reduce waste principally. A lot of people focus on the process and forget about what happens with the waste streams that emanate from those said processes, and what that really means to the environment and the community in which the waste ultimately have to end up. So focus becomes one of minimise the waste, improve the efficacy of removal, and this becomes really applicable to some of these emerging technologies to battle those known contaminants that have been around for quite a period of time. So we've been very prominent in the PFAS space. Our work on development for removal of mercury has been going on for 10 plus years. And NORMS is something that we're heavily into at the present stage. So I'm looking forward to talking further with you about that.
Excellent. So, Sasha.
Francis, good to be here. Yes, another Callaghan in the room, Sasha Callaghan, and very fortunate to be a part of the journey with OLEOLOGY and all of its initiatives that it's taken to the market, which has been fantastic. But it's good to be here.
Very good. And my colleague over in the corner there, Sean.
Yep, Sean Sadler. I'm the General Manager at CODA. Delighted to be involved in the conversation with you. We're doing a lot of work at the moment in CODA, looking at waste management pathways, and the work that OLEOLOGY does obviously plugs right into that. So looking forward to the conversation, and in particular understanding more about capabilities in relation to some of these key contaminants.
Beautiful. So if I kick off with the first material of interest, NORMS. We hear a lot, it's a very high profile. We hear a lot of discussion in the decom space around NORMS, naturally occurring radioactive materials. Paul, where are these found? What do we know about them? What do we how do we then start to manage them as we go into decommissioning?
NORMS are really interesting because the conversation is principally around the oil and gas area, but NORMS are something that have been dealt with in the mining industry, for instance, for a long period of time. So the very start of NORMS says the word naturally occurring, and that is the part that a lot of people seem to fail to realise, in a community-wide level of interest. So these materials are in evidence in lots of areas around Australia. We've become involved because principally we're able to remove the other contaminants that end up in pipelines and facilities for the oil and gas industry. And NORMS is an area that one of our partner groups that we work with in technology development in our innovations area did a lot of work with for removal of cesium as a result of Fukushima. So that proven technology has application for us as an adjunct to the other techs that we employ to treat mercury and so forth. And like any contaminant, it doesn't appear on its own in water. So the contaminant of target is often shielded by, the range of co-contaminants that exist in that phase, whether it's water or air or other. And so one has to consider dealing with potentially the oils, the BTEXs, the residual organic contaminants, the mercury that might be in existence, and then the NORMS. You can't just have one material as part of a process to try and deal with that targeted element, because in the end it ends up being blinded by the co-contaminants. So you have a short level of operational excellence before you have blinding and breakthrough. So the focus is around treating NORMS, but in order to treat NORMS, what else needs to be removed before we can get to that point where the polishing material that's required for the NORMS treatment has a high level of efficacy and service life? Because if we don't have high levels of efficacy and service life, we generate a lot more waste.
You used a word in there that maybe might be worth just going back to: polishing.
Polishing is the final stage that if we talk about water treatment, and this can be analogous to any range of contaminants, polishing is just the stage where you get to low levels of contaminant concentration residual in the water. You take those out by polishing. Everything beforehand is generally high levels of concentration removal or removal of competing contaminants that would otherwise compete for sites on the polishing material. So in order to develop a robust system, one that can treat highs and lows of varying contaminants and concentration levels across a whole range and suite of different contaminants that arise in water, that arise from different waste streams being added at different times, the nature of which we always are aware of, but don't always get the full disclosure from potential operators or clients, and not for any reason of wanting to hide it, but it's just simply not known to them, these other areas of competition. So, in an ion exchange, there are very specific ions that are targeted for removal by the polishing material. However, the performance and efficacy of the ion exchange can be radically impeded by the inclusion or failure to remove of co-contaminants and, simply like emulsions. So something that's designed to have a robust life and service period of months or years may in fact have breakthrough after a very short period of time. And we can talk about days and weeks.
So it's a case of designing the system for everything that's in the line, and then, as you say, polishing it out when it gets to, once you've captured all the, let's call it the easier to catch bits.
It is exactly that. And the great thing with the advancement of technology is the analogy that you've drawn, or the concept that you've highlighted on, is something that everybody's known for many years. But the problem has been that the technologies that have been available in order to achieve that have been very large and cumbersome, have been slow to process, and as a result of that, are not really possible. You certainly couldn't put them offshore because it just takes up too much real estate. You can put them onshore, but again, there's a large capital cost in developing that particular piece of plant and equipment, monitoring it, maintaining it, all of that. So where technology has really leapt forward is the ability to reduce the footprint and maintain efficacy and be robust. So the principle to which we work with is utilizing equipment which essentially remains as a sentinel and is only called into action in the chemical sense when the contaminant of affinity is in the water. Otherwise, it remains there inert. And so the ability then to have a robust system is one of, we can cater for a much wider range of co-contaminants in the water, treat to low levels, but before we get down to that polishing stage, we've homogenized the water. So we have a robust system that's able to treat water to very low levels of contaminant concentration at the discharge end, but that's as a result of what happens very early on in the sequence of stages of water treatment.
Very good. Thank you. This is getting very technical. It's very good. It's very interesting.
Yeah, I was wondering if, are you able to talk about the technologies or chemistries that are specific to NORMS reduction in water systems? I'm aware that there may be IP issues in that space, but in general sense, what types of chemistries do you use to target NORMS?
We use wherever we can naturally occurring materials. And so, yes, there is some IP around this. But those naturally occurring materials enhanced in performance are what we utilize. Now, a lot of the NORMS are contained within scale. So scale is relatively easy to remove. So we strip the scale out, and then you're down to materials where you're looking more at leaching. And so the interesting part about the application of the tech is that we can put it into two potential scenarios. One is to bring the material into contact with a surface from which the NORMS are going to leach. By doing so, we can accelerate the rate of which the leaching occurs. The second way is to allow the process of leaching to occur into a water stream and then utilize that material as a filtering element. So process can be adapted, and that, obviously, if you can utilize the former, whereby we bring the product into contact with the wall of a pipe, for instance, you can potentially do that in situ. And you can leave it there for a period of time. And then you can remove it and take with it the contaminants. And the key to what we do, whether it be oil water treatment or other, is in just about all circumstances, the chemistry that we utilize is fixed. It's onto a solid of some sort, be it infused into a filter or utilized as a coalescing membrane, or in this case, utilized as an infused element as part of a solid. So we can put that into situations where it's then easy to remove. We don't end up leaving other chemicals in water stream, which may be problematic in the future. It's one about not leaving an environmental footprint.
So once you've caught it, filtered it, captured it, what next?
Well, in that instance there, we've got low levels of waste in volume. Then there's other specific work we're doing with a group that are based out of the East Coast, where entrapment in an encasement into fixed structure has been shown to reduce leaching of radioactive waste. That enables us to look towards deep burial. We know there's a problem, something with a 500,000 year life or half-life of 1 million years is always going to be problematic. So the focus is, how can we put that into a situation which has least impact for the community and the environment? And so the answer lays in there. Complete answer for you? Probably not.
But really get it down to as consolidated a pack as you can, as dry as you can, clean all the water, and then find the best possible way to manage that consolidated material.
Yes, yeah. And look, the principle that guides us is the opposite of what used to be solution by dilution. We're about concentration into a very small mass. And that small mass is far easier and at lower risk to transport as a contained waste. And so we see many advantages to that for environment, community, and industry itself, ultimately, because it becomes a cost.
But isn't one of the most interesting parts that we see from oleology's perspective on the industry is what can be done in place, in the field, and not having to cut things up, not having to transport. We're trying to simplify the process where possible. And essentially, we want to demonstrate that, because has it really been achieved in the industry? Probably not. anyone's really aware of or on big scale?
That we're aware of, yes.
Yes.
I would say that, certainly that I'm aware of. I'm not aware of anyone that's achieved that yet. So no, it's a good goal. It's a good target to have that, to be able to do this. So from a regulatory perspective and from a compliance perspective, where are you seeing the landscape as that's going forwards?
That's quite a leading question.
Yeah.
It's there are many interested parties as pertain to the regulation, and as technology evolves, those regulations have become somewhat tighter. Compliance levels have reduced as far as concentrations of wastes in a particular effluent develop. We see the opportunity to be ahead of what the regulation is now and reduce the potential liability for operating companies as at now. And the big question, I think, that sits in part way to that answer in the minds of people commercially is, if I just need to treat to what's required in the regulation, and this is where the answer becomes somewhat open to a further debate, do I really need to do anything more? So on the commercial side, we say, what's the difference between commercially at a rate per kilogram or per tonne to treat to say 95% of the requirement, or treat to 99.9% of what we know is then beyond detection? So that's a commercial discussion, and because of the technology and the way it's developed, the capital cost is almost the same. The operating cost is very little difference. So our question to our clients is, what do you want? Do you want to remove potential future liability to the best of your ability now, knowing the technology that's available? From the regulator's point of view, the regulators struggle, and I'm talking generally here, the regulators struggle with the understanding of what this new challenge is in the community. So they'll be talking about a local council, or we're talking about the EPA, the people who write up the Stockholm Convention. At what level do we talk about regulation, and where and to which area does it apply? So our simple premise is, can we get that message to the regulator about the commercial availability and inform them of what is possible, and it is not commercially unviable? And we had similar discussions with the US EPA with regards to PFAS some years ago. And so it was interesting in a forum discussion with members of the US EPA across the US. Their answer was, we want to understand what the technologies are, the robustness of that technology and its capability, and commercial reality. Can it be implemented, and can industry sustain that cost? So with that, and I'm not saying that we drove the change, but there has been significant reductions in the US as an interesting case. If you look at PFAS and the concentration that's now seen as compliance level, it's come down somewhere between 10 and 100-fold, depending on which compound you look at. But certainly the range of compounds has increased. And very interestingly, and I find this very interesting, they've now introduced, as at the 1st of January this year, a method of looking at a range of contaminants and assessing the total of those by a multiplication factor. So it's not just looking at any one contaminant and its concentration and ticking, yes, it's okay. It's now looking at the range of those contaminants using a multiplication factor and saying, will it be above or below the harm level? And that's particularly an application to drinking water for them.
So there's a lot changing in this space, then, isn't it? It seems that the regulations are rationally trying to follow the technology in an affordable way to make sure that, that we don't put something in that just is completely unfeasible, while also trying to do the best we can in terms of the outcomes. And look, in some regards, you can almost take that, as you've said,
looking at what we can do now and say, do we have the best technology available now to treat, or should, in fact, we wait? Because as some of the emerging technologies come to the fore, and we've only got bench scale, is there the possibility that technology at bench scale can, in fact, be developed to industrial application? Because if that's a feasible answer, then perhaps there's reason to actually wait 12 months.
Okay, so that maybe we move on from norms. Another material of concern, another one that comes up a lot is around mercury. What are we dealing with here from a mercury perspective?
Well, we're either considered lucky or unlucky to have an abundance of gas, but also to be one of those few countries that are tormented with mercury being in our oil and gas fields. This region through here heading north, I think there's a few spots over around Germany, and there's a couple of other spots around the world, but we have mercury. Luckily, we have, through Miselex and the innovations that they've developed over the years, the ability to treat mercury, not only to treat it, but to understand its speciation, more so in water when I talk about speciation as compared to gas. But there is an available technology now that we have utilized here in order to remove mercury from gas. And we've done some analysis work on that. Compared to conventional mercury removal units, which are very large in size, big in capital cost, and generate a lot of waste, the Miselex MERCEP unit is very small in footprint, is able to coalesce mercury from a gas stream with very little contact time, very little pressure drop. So we're able to then remove mercury almost at will from gas in either gaseous or vapor type states. In addition to that, we end up with mercury in other forms in wastewater. So in the waste and produced water, mercury tends to make its way into an elemental in a small percentage, colloidal, and then ionic mercury. So the technology that we have now allows us to speciate that, so we understand what form the mercury takes within a water stream, and as a result of understanding it, we're then able to apply the correct level of technology to remove that from the process. So that's in treating it in conventional systems. Similarly, I guess, when we get into the area of decommissioning, we see mercury in scale inside pipes. And so as a result of leaching that out, mercury will come out in its various forms as well. So firstly, understanding what form it's in is key to understanding how to best remove it. From there, we're then able to develop and design the system in order to treat those forms of mercury and the co-contaminants that might exist with it. Because where you're dealing with the mercury, you're also certainly dealing with the other organics. The reason why the industry was there, first of all, they weren't there to discover mercury, they were there for oil and gas to provide energy for everybody. So you have to consider that they are going to be there in some shape or form. So again, you get into that process of how do we make this robust? How do we make it high in efficacy, high in efficiency, and a high level of certainty for compliant discharge? And that's by stage sequence.
You talked about technologies for controlling and managing mercury during production. How widely is that being deployed, and are there any examples that you can point to?
Our technology, Miselex technology that we work with, hasn't been employed widely across the industry. Convention has been with mercury removal units, and they've been around, as carbon has been around 150 odd years. So they're somewhat of the go-to, and it's having having a conversation about removing a contaminant from a production system is not an easy one to begin. No one likes to admit that there is a significant problem that they've got, and certainly to an outsider, without necessarily having been invited in to go and talk to clients about potentially we can assist with mercury removal, and the shutters come up. So it hasn't been widely deployed, but where it has been deployed, it is very significantly removed and fixed problems by literally removing conventional coalescing condensate coalescers and applying the MySelect system in place of those coalescers.
What is the sort of end product of the process, and what do we do with it? You know, how much it gets created and condensed, and what can we do with that waste?
That's a really good question, and it might seem to anybody listening to this that you've been set up to ask that, but it's not the case. So if we talk about a conventional system, we will end up with 10, 20 tons of mercury contaminated waste. By contrast, the MySelect's coalescing element has a long-term in application, and because of the way it works to coalesce the mercury alone out of the gas stream. So the waste that is generated is elemental mercury, and that by volumetric size is probably, hundreds of litres at the most, compared to thousands of tonnes. So it's far simpler to deal with, and it's interesting to note that mercury in itself is a difficult product to gain now, and it has application in other industries. So it has a growing value in some commercial applications, industrial applications now.
And I think as well with, I suppose, those that are aware of what oleology has done for the past few decades, and then they become exposed to this new branch of what we can provide for the industry in regards to mercury, there is that level of knowledge that we're imparting to them that this is actually, it's not a filter that Paul's alluding to. It's very much something that is meant to saturate. It's that coalescing form of that mercury. And that's why we're able to capture it. And there's rippling effect of other benefits from there. And even for that processing application, and there's benefits as well down the line when it comes to the decommissioning phase for any site, but you're able to then alleviate that form of embrittlement, that full downstream causation of impact by mercury. Paul, you're looking very keen to say something.
No, I'm looking very keen for you not to say something. Certain things that we can talk about, and a couple of subjects that we can't go into.
Fair enough. So it sounds then that through all this, we're actually seeing mercury almost as a product, as a byproduct, rather than a contaminant. And if you can capture it in the right way.
Yes, and we're in that circular economy. So we're in a state of mind at the present stage where what was someone's waste is now the opportunity for reuse. And that is definitely an opportunity within here, particularly if you take pure elemental mercury. It is a valuable commodity. If you look at it on the commodities chart, you'll see that its value has risen quite considerably in recent times. So the opportunity, and go a bit broader than mercury, is to look at those other products that are considered as waste. And conventionally, we would just say, just grab it with whatever you can, blot it up, and we'll bury it. Now we're saying, is there a way that we can take the amines, the phenols, the mercury, whatever it might be, can we take those? Can we separate them? Is there a way that we can capture those, allow the other co-contaminants through, and take that value back and put it back into the community? you see it broadly. I mean, we're sitting here with bottles of water in front of us. They've got a 10-cent value on them. Empty, not full.
Yeah, I think to open up, again, focusing in specifically on decommissioning and the decommissioning perspective, we've talked quite a lot about prevention and capture of mercury in production streams, but in decommissioning projects, we're often looking at older infrastructure. Those prevention mechanisms weren't in place. There is an element of mercury contamination. Some of the key challenges that are being looked at the moment is understanding the distribution of mercury in existing infrastructure and the potential to clean that in situ before you take it out. And would be interested to get your perspectives on that, about the feasibility of technologies operating in an in situ context for detection and cleaning.
We are very interested in doing things in situ. And if we go back in the history of oleology, a lot of the equipment that we've made available to industry, and it's somewhat been considered as unconventional because of its small footprint. So it's just as easy to deploy it to the field as it is to build it into a depot and bring the waste to the depot. So similar principle applies here. So we've got an unconventional but very small footprint of a robust treatment system. So can we collaborate with the right service providers in association with the clients to actually look at the decommissioning space, evaluate through a front-end design to see what is potentially possible? And so the answer to your question, that is not what you were looking for, I don't think, Sean, but that's the reality of it. So it really is that collaboration that we seek to do and undertake with others. No one understands the potential products that we have and the innovation and research and development work we do around those products for applying them into different circumstances. So we need to clearly sit at a table in fairly frank and open discussion with the clients, and they need to outline to us what they want, what they would really like to do ideally. That ideal world, then we can look at and say, are we able to do that with these potential products? And if it is in situ, because ideally you would clean up in situ, reduce the waste contaminant before cutting and transporting, that makes life a lot safer and better for all, then that would seemingly be an ideal situation. Does it also bring open the opportunity that perhaps some of this materials that are assets presently could perhaps remain in place, not disturb the environment? I think it opens up a discussion around that and potentially what is the upside and downside for both of those. And it has to be done in a way that's not imbued with just emotion and not imbued just with commercial considerations, but it's arranged from both of those ends of the scale.
I think your reference to the importance of the type of research and development that the oleology does is reflected in the fact the industry. We asked the industry, or at least the operators, what their key problems were around decommissioning, and the current Explore challenge. CODA's open innovation platform currently carrying a challenge looking at how we potentially measure in situ mercury contamination in pipelines. That reflects the importance of really getting in amongst this and thinking differently about some of these problems and how we deal with them in different contexts, as you've said.
So that brings us to the other material that we've touched on as we've gone through all of this, and that one's PFAS. And PFAS was really where I first met you guys way back when, and with the work that you were doing in that, in the context of decommissioning, but maybe more broadly as well, just for those who aren't necessarily as familiar with PFAS and what it is and what it means. Can you talk us through a little bit about what it is and what you're doing with it and so forth?
Well, PFAS has been around in the community since the 1930s. It's a synthetic organic. It's got some magnificent properties. Your pizza box doesn't leach oil through it as a result of PFAS. Your brake fluid doesn't overheat and oxidize because of a PFAS compound that's added to brake fluid. The range of lubricants that utilize PFAS is very wide and broad. Teflon tape has a very basic number, and Teflon in its utilization gives great lubricity to things. It doesn't break down with heat. It doesn't break down with changes of pressure. And so those same properties, which are brilliant in the application that it's desired for, and that is, sealing pipes, making things more slippery, preventing oils from penetrating into areas you don't want them to go. All of those particular elements, and not breaking down under heat and pressure, are the same problems that, when it ends up as a waste, means that it lasts in the community for somewhere between 9 and 40 years as half-life. The IP that's surrounding many of the PFAS compounds is still unknown. It's very tightly held. Peak production of PFAS, the two key PFAS compounds that we concentrate on, PFOA and PFOS, was in fact in the 1990s and the early 2000s. And those two compounds I mentioned, they were manufactured at the rate of about 10,000 tonnes and 50,000 tonnes respectively in those periods of time. So peak production now has scaled back because the use of PFAS or PFOS, one of the keys, in firefighting foam has now been somewhat regulated against and is being withdrawn from operational use. However, there are 7,000 PFAS compounds, and the compounds themselves change state as they very slowly oxidize. And to put that into perspective, PFAS has health, is detrimental to health in many ways, and so there's a lot of work that's been done over many years, and it's an endocrine disruptor. It's linked to various cancers, and so the work that we've been doing is to be able to remove these compounds broadly out of waste water, particularly. It's highly soluble. So, in terms of solubility, oil will separate out from water and sit nicely on the surface so you can scoop it off. Benzene, when you get to the other end of that spectrum of hydrocarbons, is somewhat soluble. And I say somewhat, and it is soluble, somewhat when compared to PFAS. PFAS is highly soluble. You can look at water, and it can have high concentrations of PFAS in there, high in terms of the detrimental health level concentrations. You won't see it, you won't smell it, you won't know it's there. The interesting part about that, and the reason I mentioned benzene is highly regulated. It's known to be cancerous. So it's regulated in its availability into the community, and principally it's been used in petrol for many years as the go-to for ease of start. However, you release benzene into the atmosphere and it'll break down to its component parts of carbon dioxide and water vapor, basically, with the addition of UV and pressure and temperature. And that'll happen over hours to a few days. Go against PFAS, which has 9 to 40 years as a half-life. And the big difference then becomes one of, you release benzene, over a week it's gone. You release PFAS, it remains there. you release some more PFAS, it accumulates, and it continues to accumulate, such that now a product that was only been around for 70, 80 years is ubiquitous. It's measured in the world's ocean. It's measured in rainfall. It is everywhere. So compared to benzene, it seems simple.
So in the context of decommissioning then, it's not something which occurs naturally in the stream of product as we get with NORMS, as we get with Mercury. It's something which has been used in the assembly of the equipment. And then as we disassemble the equipment, we need to make sure that we're capturing and it's not ending up as discharge or unintentional discharge. Is that fair to say?
That is very much the point. It's very much the point. So because of its ubiquitous nature and there's so many products that it's contained within, that it can inadvertently become, it can leach out of the materials because it's something that's been used at another part of the process. So it can be in a pipeline and it can leach out. And to give you an example, in some of the fire training grounds that we've got water treatment plants on, some of those grounds, concrete, have not had a live fire training exercise for nearly a decade. They're in high rainfall areas. So you would think by the time of 10 years has passed that the PFAS would have leached out of the concrete completely. Not the case. And something that's regulated down to 0.0002 parts per billion, we're still getting measures after some rainfall events of 300 parts per billion. So it's leaching out like that. So the point is, it is great in some applications, but it's a problem in others. And it's more of a problem when you get to the point where you now start to decommission and you start to look at those co-contaminants. What else is a problem for us? If we're going to be treating and removing the NORMS and removing the mercury and taking out all the naturally occurring organics, and we're about to now open the valve to discharge into the environment, and someone comes along and says, wait, have you tested for PFAS? The whole of the treatment plant comes to a standstill because there are very, very few instances where we've tested for PFAS that we haven't found it. And the more you go into the industry types, the more you find it there in higher concentrations.
If one of the perspectives that we've seen, not necessarily in Australia but elsewhere, relating to oil and gas, particularly in an onshore sense, is around site remediation. As sites are being decommissioned or treatment plants are being decommissioned, there's a question comes up around PFAS. What are the options for people to deal with PFAS contaminated sites?
The present options are to try and bind it into the soil and prevent it from migrating with groundwater. And that surely would have been a great benefit to the people around Williamtown and Oakey air bases and for around Tyndall, as we know what's happened in those locations. And that's as a result of fire training exercises, spill off, foam. Everybody thought it looked great as it billowed across the ground with the wind. So bind it below ground in the soil and prevent the problem from migrating, and that's a great start. Barriers to movement are a significant improvement on doing nothing. The ability to extract water, treat the water and discharge it is also an opportunity to mitigate the potential for this product to remain in the environment and spread. And the third option, which is the holy grail, is to be able to treat the soil. Now, there's been a lot of work done in that area by a large number of people through industry and with military, both here and other places around the world, to try to refine that possibility. It's relatively simple to do in silica-based soils, but when you get into the loams, it's far more difficult because of the product that we're dealing with itself and its adherence into those loamy soils. So PFAS makes its way through to with groundwater, sits on the clay, migrates across the clay in the geology, and as a result of that, you end up with the clays, which are the fines, holding the PFAS. So the technology that we're currently working with and doing some developmental work for those types of applications, it's a possibility to treat, because it can treat particles up to about 30 millimeters in size. So there is a potential way forward, but we're not there yet.
Is there a chance to talk more generally about existing commercial solutions for PFAS treatment?
Which is probably more in regards to the liquids, yes. There is methods of treatment such as foam fractionation, which can handle higher PFAS levels. However, but then you go into, well, what are the regulators requiring? And that's low level or even complete removal to where labs are able to test down to. Then you've also got very common methods, as Paul's alluded to, carbon, very common method of treatment for a lot of water treatment plants. And you've also got ion exchange as well. And that's really where Paul actually was driving the ship many, many years ago, when it was not known, especially in Australia, in regards to commercially viable treatment methods, that Paul started actually investigating on the PFAS removal and the technology application and process for that, which where we stand right now.
This is the penultimate discussion about co-contaminants. So in wastewater, and a lot of that peak production we talked about before, the 90s and 2000s, a lot of those products have now ended up in landfill sites. Landfill sites with leachate have a very, very complex range of contaminants, which all need to be considered when you're trying to treat the most soluble of those organics, being the synthetic organic. So it's the perfect discussion point, because within as it pertains to oil and gas industry, there's a full range of organics in the complex makeup of oil and gas. So treating the waste out of a landfill leachate, you end up with high levels of biological activity. There's oil and grease, ammonia, and then a range of dissolved solids before you start considering tannins and other very short-chain hydrocarbons that all need to be treated. You can apply carbon to it, and you can apply a lot of carbon, and it will work, but you'll have breakthrough. And what we see is short-chain PFAS breakthrough very early in life. So without generating a lot of waste, because then you've got to treat all the waste, how do you do that? And that's the range of filtering products that we actually have. The interesting thing, as we go back to the earlier discussion about mercury, is if mercury is in that same leachate waste, we can remove the mercury in addition to the PFAS, in addition to the hydrocarbons, through the same treatment train. So the ability to have complex wastes removed by the same treatment train is where there's a significant technical advantage to the application of this MySelex technology, and the development that we've done with MySelex on the infused range of cartridges and their particular applications. There's no online ability to treat, there is no online ability to be able to monitor for PFAS. It has to be done in a laboratory. So the biggest challenge for us at the present stage, and for us being water treatment industry, is being able to infer the level of performance and whether the polishing media at the very back end is still operating to its starting point. That is, are we still compliant in our discharge?
It's interesting that you talk there about disposal and PFAS finding its way into landfills and things like that. If we were in a situation where we've applied this technology, we've actually captured some of this PFAS and consolidated it, what are the best ways of disposing of it?
In this instance here, because of the media that it's captured on, we can take that small quantity, and we are talking about a small quantity, and we've had sites operating for 12 months, and we might generate something the equivalent of a pallet of cartridges. That can then go to thermal oxidation, high temperature combustion, at which stage you're able to burn those things relatively simply. And you then end up with elemental discharge, being fluorides and water vapors and carbon. So that's the safest way to get rid of it. It's total destruction of the long chain synthetics.
And that's the part of the equation that I believe a lot of industry are forgetting to ask the questions. And when I'm discussing, because a lot of our clients come to us and say, look, I have this problem. How can you help me? And a lot of that knowledge and questioning is, well, have you obviously considered all of the commercial points of implementing such technologies and understanding their limitations? But also, have you asked the question of how much waste am I generating, and also the costs associated with it? Because there is a significant difference between a sludge that is contaminated compared to a smaller, drier waste. And that has been ultimately the game changer for a lot of different industries, even civil construction, where they're having to do a lot of dewatering, and you're dealing with legacy sites that no one even knew about, which will ultimately come up as well in decommissioning areas and using other sites that have been used for other applications as well.
Which really goes back to your earlier question about contaminated sites and how to treat it. So because of footprint and waste volume, there is a significant opportunity to put in small systems that continually flow, treat the groundwater. You can put it back, a proportion of that back to ground, and allow that to essentially cycle through almost like a washing mechanism.
No, I think the really interesting piece there is around understanding the scale of the waste product at the end of it. You're saying you've got something operating for maybe 12 months and you've got a pallet's worth of waste at the end of that, and I think that's really good context.
It is. It's, and as Sasha said, often the clients and we ourselves concentrate on the process of taking the bulk of the fluid, treating it for the contaminants of concern, perhaps some of the co-contaminants that need to be removed to give it the robustness, and making sure the compliance is in the discharge. But when you look down the length of that process train, that's great, and understanding that we've got compliant discharge, but coming off that process, you have to consider what are the byproducts that come as a result of that treatment, and how am I going to capture it, hold it, potentially transport it, or what other process is going to need to be added at site in order to treat that before I can then have a waste that is something that can be handled.
Actually, really interestingly, the insurance industry are now starting to focus on the PFAS contamination. And then when we start talking about risk management of, okay, we're transporting it from A to B, but also then you've got legacy sites, the ownership of who's owning that site, managing it, and that downward trend of, well, who's managing all the different waste and byproducts is a real consideration that is getting a lot of attention now.
And it comes back to that, I mean, I'm going back to my early years within the oil industry and just thinking, I remember one of my colleagues telling me about a service station that was about to be sold, and someone he knew was considering purchasing it. And at the last minutes, and this is going back into the early 80s, someone said, "Oh, wonder if it's contaminated." So the upshot of that was that the they took some soil samples and found there was contamination, very significant contamination. And then there was an underground stream. It was a country location. There was an underground stream, so the plume had spread extensively across the site. So the site was something for sale for $350,000 or something about that. The cost to clean up was put at $320,000. And what happened as a result of that, going through that part of the industry at the time, was there was a significant review on potentially sites that might be contaminated because of their age. And if banks had loans provided to those site owners, what that meant to the value of their loan. And some of those loans were called in, or there was a requirement for site analysis to be done to ensure that they weren't contaminated, because essentially they were worth nothing, or perhaps there was a greater liability than there was an asset.
Well, it is, isn't it? It really is. That's sort of the future of a lot of different industry sectors as we get into that particular area. Well, look, those three have been absolutely fascinating as specific areas. What are you seeing as the trends? Where are we going next, and maybe around the three, either separately or all together?
We'll start on PFAS though. The US are definitely leading. Interestingly though, the EU have made some really interesting steps forward and actually wanting to eliminate in the production and use of PFAS compounds in their manufacturing, which is huge. That's a very, very gutsy move, I would say. And they wanted to achieve that by 2030. The US EPA are leading in regards to setting those regulations, and Australia is very much looking at that, following it closely. We're seeing some of that rippling effect over into the Australian EPA and its regulators. But also there's a lot of question marks from other industries that they're not sure where to go. But we continue to watch the space.
I think the application of some of the technologies, any one of the three that we've talked about, or contaminants that we've talked about, is something that will be more of a consideration of inclusion in the early design phase, ideally. Why contaminate something if you can prevent the contamination from occurring? Is that possible? Well, that's what the innovation and design part of our group is about. So if that were possible, then I think that is a far better answer, because then it reduces contamination of assets from day one. It means that the potential cost of cleanup at the end of life ceases to be an issue. And end of life considerations with changing drive for energy is something that I guess everybody's looking at. So life of a field and its commercial value will change as a result of what energy source is sought by the community. And some of that is preordained. I mean, we've got the discussion now about, is nuclear going to come on? So who knows what that's, governments prone to make changes. So all of that begins to have an impact on how you begin to view what's done and when do you do it in this light. So I would say Mercury and NORMS. Can you remove NORMS from a gas stream? No. Can you remove mercury from a gas stream? Yes. How do you apply those things? That's the next stage. What can you do with PFAS? Well, it's more of a contain and control. There are some areas where there is no alternative at the moment known to us. That changes with the drive to develop that. So you put in those guidelines, and technology will abound to satisfy it for sure.
Sounds then that there are maybe 2 or 3 different life cycles, if you like, that we're talking about here in terms of the technology use. One is catch it before it gets there in the first place, which is design it in, which is really good for new facilities or modifying facilities where that maybe hasn't occurred yet. The second one is, what do we do with the material if it's already got into a pipeline, it's already got into a piece of process equipment? And then for me, the third one, which is probably the shortest cycle time of the lot, is the cleanup technologies associated with, okay, now the material, the contaminant is there. We removed the material, we brought it to a facility, we're going to clean it up before we put it off into its next life. So we send that steel away, we send that plastics away, we send whatever the other things are away as well. So 3 quite different application spaces for the technologies that you've got. Where do we start?
Ideally, you would start at the beginning. So if it's a greenfield, you would apply now. Brownfield application, if there was a way to interpose technology to reduce the contaminant level, that's a sensible, possible achievement. That then comes down to field life and the possibility of intervention. Certainly in terms of the beginning again of the decommissioning phase, really for Australia, we're at the front end of that. So getting it right now and capturing those wastes and doing it economically for the benefit of the industry, it may well be something that an industry established in Australia might have application for others in the region.
Indeed. Yep. And we cannot forget that it's not just us. This is across the regions, across the world, that everybody is looking at these same questions and same challenges.
We're having discussions out of our office in Malaysia with operators there, and it's interesting that they are keen to understand more of what we're doing, at a local level and a technology application specific, which is really encouraging for us as technology providers. We went to one of the nations nearby back in 2018, spoke about PFAS. The water corporation equivalents there were unaware of it at the highest level at all. It's now become a community discussion point. So, and that's 6 years. So in that period of time, there's significant change. Significant change similarly in their discharge compliance for water with hydrocarbon. That they're looking at reductions of 25 to 50% compared to what we were at in those same time frames back in 2018. So I think every community wants to have the same outcome. They don't want to be the ones that are sitting with the waste lapping at their shores.
Just looking forward now, I mean, are there any upcoming projects or initiatives, again, even in the R&D space, that you would like to highlight? Is there any single particular one that you'd want to single out and talk about in terms of what's coming?
As an Australian sitting in on this discussion and talking about how can we make our industry, that's our oil and gas industry, I guess better in a very broad term that is. I think the application of the ability to coalesce mercury out of gas at a low cost is really important for the industry, and that potentially can be beneficial to the operators. I see that as a win for all. Yeah, and I think if we're looking at the oil and gas space, that would be the one, and certainly if we could find a way to apply some of the technology, as we were saying earlier, to in situ removal of NORMS, such that we didn't disturb the seabed any more than had to be done, because some of these assets have been in place for 20, 30, 40, 50 years, and we're able to leave them, then that could be advantageous. I mean, we don't go around tearing out the Bismarck from the English Channel and likewise for a lot of other wrecks that are around the world, that they have a place. My personal view is the ecology and what happens below on the seabed is continually changing. There are massive eruptions and other things occurring below sea. We're discovering new areas around there. The need to go in and destroy some of that seabed for an unknown gain at this stage seems to me short-sighted.
And I think you previously mentioned the circular economy perspective, and from a decommissioning angle, the circular economy would mean designing for decommissioning, design for optimized decommissioning. Imagine if we could take the threat of, for example, mercury contamination out of the equation somewhat by getting that controlling technologies in place up front during the production phase. I think that's key to unlocking a bigger picture circular piece for the industry more broadly.
Always. Anywhere we can take an improvement at the beginning of the production, the benefits flow on, in not only directly but indirectly. There's significant cost savings for everybody and improvements for community and environment.
But going back to your point, Sean, on the R&D activities within oleology, maybe we should circle back in the near future and we'll be able to share some things as there's a very big steel door and armed guards in front of what we're doing. So we'll let you know when we're able to open the gates for you and share some of our activities happening behind those doors.
Absolutely. That sounds exciting and quite scary too. But
we've put a lot of activity and focus on the R&D space, and rightly so, because there is a need. We don't necessarily want to develop something because we think it's a great idea. It's actually got to be a need and a drive by industry from both sides. Is it commercially viable? But also, is it a need as well when you look at it from the side of the regulators, as an example? So we are actively, and we've actually got a full-scale team on it, and also working and collaborating with other subject matter experts in various fields, not just within Australia, but also across the seas. So that is important, and also to bring that skills and knowledge into Australia, and that's important as well to further drive not just the oil and gas industry, but any other industry within the Australian economy.
I think that feedback loop that you talked about with industry, between industry and yourselves as researchers and developers, is incredibly important, and prioritizing things which are meaningful to industry is also incredibly important and really the way forward.
Geez, we've covered some territory here, haven't we? So, anything you'd like to raise with us while you've got us here on the microphones?
I think the key for us is how CODA can get an open and frank discussion between people like us who are technology providers, who actually see potential opportunities in a forum where the non-disclosure, but there needs to be the ability to open up. And so from the operators, if we're talking about the oil and gas industry, so the operators can talk about what they see as their driving problems. As Sasha said before, we don't want to be developing the widget that we think industry needs. We want to develop the way to achieve what the industry seeks. So if between the regulator and the clients in the oil and gas industry, if we can get a better understanding of that in a kind of unfettered discussion forum, that would be something that we would like CODA to be able to facilitate.
Okay, I'll have a go at the first bit of that, and then I'll pass over to Sean to maybe talk a little bit about what we've got going on now. I think there's a couple of different phases and stages to this. The first one is getting the whole of industry, not just the operators, not just the service sector, not just the regulators, the whole of industry, to really mobilise around the work volumes that we've got in the decommissioning space. I think that's happening now. When I think back 3-4 years ago when we were getting CODA started, there was still an understandable level of apprehension across the service sector side that when the work was going to happen, what it was going to look like, what the expectations were. The regulators themselves were still trying to get their arms around just what it was they were regulating and what it looked like. And the operators were dealing with just the volumes of work that they had coming up. So I think, first off, we've got to do that. And I think there's been a lot of progress. And I'd like to think we've had a piece or a part to play in that evolution and moving the discussion forwards. The second bit is just making people aware of where some of these smaller pieces, if you like, in the overall picture of decommissioning. Because you look at it from a holistic perspective and it's about removing, plugging the wells, closing the wells off, removing infrastructure, bringing the infrastructure ashore. And for a lot of people, that's what they see as being the whole life cycle. Once it's got to shore, it sort of goes out of sight for some parts and comes very much into sight for other parts. So having that awareness across the whole life cycle is absolutely critical. And then getting into that and saying, right, along that journey, we've got to deal with contaminants, we've got to deal with different waste streams, we've got to deal with different material streams. And we call it all waste. But realistically, around the world, 95% of everything that gets removed gets recycled. But the more we can move that 95 to 96 to 97 to we reach the point where we've recycled everything that's economically viable is really important. Thereafter, it's having, as you say, it's being able to facilitate those conversations. And Sean's been doing a lot of work in that space in terms of trying to bring, let's call it the decommissioning community together to have these conversations. Do you want to talk a little bit about that, Sean?
Yeah, I think in a more general sense, CODA is all about, one of the foundation principles of CODA is about creating non-competitive collaboration environments in which we can have these open conversations. I think particularly though in terms of dealing with what are perceived to be contaminants, there's a certain amount of sensitivity which we can all appreciate in relation to that. And specifically in terms of how it is communicated more broadly into society and the community. So if there is any reticence on the part of any elements of the industry to talk more openly about that, then it's understandable from that perspective. One of the things that we are trying to do, or at least the organisation that sits next to CODA, the National Decommissioning Research Initiative, is trying to do is actually use scientific research to provide information and empirical tests of the impact of potential contaminants on the marine environments, for example, which starts to actually demystify the communications into the broader public environment in relation to these contaminants, and can start to better enable a more open conversation around it. It becomes less threatening to the industry to talk about it, and it builds a broader understanding of what we are trying to do and what the industry is trying to do, which is to be proactive in the way that it manages the challenges of decommissioning in a very sustainable sense and in a long-term sustainable sense. So the work that's being done in terms of building conversations between operators and regulators, between the community and the decommissioning providers, all play into this in terms of reducing the perceived levels of threat associated with contaminants, and building the understanding and the commitment of all different parts of the industry, and the opportunity for communities to get involved in managing outcomes which are positive and sustainable.
I'm looking at the others to see if there's any more questions coming, but yeah.
I guess the one other question would be, we've talked about PFAS, we've talked on NORMS, we've talked on Mercury. What are there other areas of concern for the decommissioning?
Or contaminants?
There are. The top of my head, the one that comes to mind is around what we can do to find a recycling pathway or a greater value for marine growth. marine growth is there, it's present. We have very, very large volumes of marine growth in Australian waters, thanks to the high nutrient levels, high ultraviolet, nice and warm water, and so forth. A lot of that marine growth, though, is on marine structures which were treated with antifouls that maybe we don't want in our food cycles. So finding a way where we can deal with things like that doesn't just result in landfill or incineration, I think is certainly one area that comes immediately to mind. But thereafter, I am sure that pretty well everywhere we look, there are going to be materials that we're going to have to try and find the best use for. The contaminants people talk about the most, though, are the three that we've discussed here.
But I mean, also what the industry is dealing with is things which are less high profile, things like sludges, hydrocarbon infused sludges, and volumetrically they are by far the thing that's front and center with in terms of what the industry is having to deal with. Yeah.
Just on that, I mean, that's another interesting area for what's behind the steel doors and the security guards, and the ability to treat those types of sludges. That's particularly the field where the application is. So it's understanding those. And as always, the devil's in the detail. I mean, you drill down into anything, and across the top it looks fairly simple. We pick up large pieces of asset and move them to shore, and it's out of sight, out of mind. When we start treating and cutting, devolving, getting it back to its base elemental form, and then we begin to see, well, with those level of contaminants, the anti-foul, if it's a typical deblating anti-foul of copper type, then we can't allow any of that to discharge into the estuary or the river or the sewer treatment plant, because that needs to be treated. And so that high level of review, and in order for us to be able to add value to the discussion, we need to drill into each of those particular elements to see where we can add value with technology as it is now, or what can we develop in that technology suitable for future.
And I think that's, the work that we're doing at the moment, looking at the requirements of waste management right across the industry, has involved us asking both operators and contractor communities what they see as the biggest challenges and what they see as the primary waste streams. All of that will be reported out, and it'll be an interesting perspective to look at, how the different groups rank the different elements of that waste, those waste streams.
Well, look, two things supposed to finish off with. First off, if people have become very intrigued with what we've been talking about here and want to know more about what you do and what oleology is all about, website, contact details, LinkedIn, email, what's the best way for them to get you?
Look, we definitely don't put up any barriers to contact us, unlike our R&D department. But yes, always feel free. We're active on LinkedIn. They can send us an email. Probably the best email, quickest response we can get through is sales@oleology.com.au. Got the full team on that. Or by all means, if you want to send us a phone call, the number is on the website.
Very good, thank you. And look, beyond that, just thank you both, Paul and Sasha, for your time and your insights on this, and Sean, of course, for your co-contribution for the questioning. Look, this has been fascinating. There's so many rocks to turn over in here, and things underneath them, then more smaller rocks underneath those. I think we could probably talk for a lot longer, but an hour is probably about right, I think, for this one, for the recording. For the listeners out there, thank you very much for bearing with us. I hope you've got something from it, and we will be back at some point with the next episode. Thank you.
Thank you.
Thank you.
Thanks for us.